Hi, in today's lectures, we are going to study the methods to analyze the so-called statically indeterminate axially loaded members. To start, let us consider a bar on the screen, which has two fixed supports at the two ends. Suppose an axial force of 600 newtons is applied at color C. Let us see what will happen. As you can see, the force caused a displacement of color C. Tension in segment AC indicated by the red color, and compression in segment CB indicated by the blue color. Now, let's say we want to determine the support reaction at point A and point B. Let us see how we can answer that question. Based on what we learned in statics, our first thought will be to use the equilibrium equation. For that, we need to complete the free body diagram for the member by drawing the reactive forces at point A and point B. Based on the deformation of the bar, we can see both the reactive forces pointing to the left. Now, if we write the equilibrium equation for this free body diagram, we will have the following equation. As you can see, since this equation has two unknowns, it is not solvable. That means we have to base on something else to answer the question, instead of a solo use of equilibrium equation. In solid mechanics, this type of problems is called statically indeterminate. So let us try to find that something else. If you notice, we can base on the displacement delta of point C to develop one more relationship between FA and FB. Specifically, since point A and point B are fixed, that delta is the deformation of both segment AC and CB of the bar. In other words, we can write the following equation. Verbally, we can say the sum of displacement of C relative to A and the displacement of B relative to C is 0. If we rewrite this equation using the equation that we learned in the last lectures, we will have the following. As I mentioned in the previous lectures, when doing algebraic addition, we need to be careful about the sign convention. To be specific, since segment AC is in tension and BC is in compression, the normal force in AC should be positive and in CB should be negative. Now let us find the relationship between these normal forces and the reactive forces at A and B, the unknown that we need to find. First, if we cut through segment AC and plot the free body diagram for the left portion, we can see the normal force in AC is equal to FA. Second, if we cut through segment CB and plot the free body diagram for the right portion, we can see the normal force in CB is equal to FB. Then, taking the sign convention into account, we can rewrite the above equation to be. As you can see, this equation also contains FA and FB. It's used along with the equation on top will allow us to find FA to be 400 newtons and FB to be 200 newton. So you have just seen a procedure or process to solve a statically indeterminate problem. This procedure is usually called the conventional method. In the following, we will study another, the so-called force method, to solve the problem. However, before doing that, we need to understand the principle of superposition. This principle is often used to determine the stress or displacement at a point in a member when the member is subjected to a complicated loading. Its idea is the following. First, we will divide the loading into components. Second, we will determine the stress or displacement at the point of interest caused by each load component. Finally, the resultant stress or displacement at a point will be determined by summing all the stress or displacement calculated in the second step. To illustrate, suppose we have a beam subjected to two loads, one concentrated and one distributed loads, as shown on the screen. Then to find the stress or displacement at any point in the beam, we can simply find the stress or displacement caused by each load separately, and then sum them up. Now, as you may guess, two conditions have to be satisfied to use this principle. First, the loading must be linear related to the stress or displacement. Second, the loading must not significantly change the original geometry of the member. For example, let us take a look at the following situation. As you can see, the beam is severely deformed because of the load P. Then the stress at the point at the fixed support of the beam will not be the same as sum of the stress at that point caused by the following loadings. The reason is the bending moments at the fixed support are not the same for the two cases. Now let us apply the principle of superposition to solve the above problem. For that, imagine we replace one of the support by the corresponding reactive force. Suppose we do that for the support at P. Then, based on the principle of superposition, we can divide the loading into two components. One is the external load and the other is the support reaction FB. Now let us see the deformation of the bar overall and the deformation of the bar caused by each load separately. Since the overall displacement of point B is equal to sum of the displacement caused by the external force and the displacement caused by the reactive force FB and is equal to 0, we have the following equation. For clarification, delta P is the displacement of point B caused by the external force, and delta FB is the displacement of point B caused by the reactive force FB. This equation can be rewritten based on the normal force in each segment of the bar. As you might wonder why we use segment AC to determine delta P and the entire length of the bar to determine delta FB. The answer can be found from the diagram for each separate load case. As you can see, while the external load produces tensile stress and elongation in segment AC only, the reactive force FB causes compressive stress and contraction of the entire bar. Now we can easily find the normal force in segment AC for the case of external loads. We can rewrite again the equation. From here, we can find the reactive force FB being equal to 200 Newton. Finally, we can base on the equilibrium of the entire bar to find the reactive force FA. As you can see, we obtain the same result as before using the conventional methods. Since we replace a support by a force in the method we just described, it is usually called the force method of analysis. To make it shorter, some people might call it the force method. Now let us conclude this lecture by comparing the conventional and the force method. As you can see, while the conventional method based on the equilibrium, compatibility, and load displacement relationship to develop a system of equation of unknowns. The force method uses compatibility and load displacement relationship to find one unknown first. The equilibrium equation is used at the end to find the remaining unknown support reaction. Having two methods in hand, it is up to you to decide which method to be used for solving a specific problem. That's all for today. Thank you and see you in the next lectures.